Hello everyone, it's Farzana Rahman and I'm going to present you the Levenshtein distance problem described in this presentation. So at first, I'll explain you how this edit distance is defined and give you a short insight into the string edit distance, also called Levenshtein's distance. The edit distance defined as the shortest sequence of edit operations which transforms x into y. As edit operation, you can use a deletion, insertion and replacement. If we talk about the Levenshtein distance, which is a string edit distance, these operations are executed on characters. So let's take a look at an example. We want to transform is the word moon into the word lions. Which operations do you have to perform is that, first of all, we replace the M with L. So from moon we got the word loon. Then we replace the second character O with an I. The next two characters O and N we don't need to change. And finally we have to insert an S and get the word lions. If we assume each operation costs 1, then the minimum edit distance between moon and lions would be 3 because we performed 3 operations. Now here comes when we compute with this dynamic programming known as standard algorithm, which is a tabular method of computation. This is a dynamic programming table and its cells are subproblems. The yellow one, it's the distance between MO and L, and the red cell means the final answer. The capital D denotes from formal way of capital distance, and I denotes the index of the substring's last letter. In this case, the index is the first O from the moon, and J denotes to the index of the substring's last letter from the other word, and in this case it's 1. So yellow cell denotes minimum edit distance D of 2 and 1, meaning between MO and L. So do the red cell with D of 4 and 5. Lambda here denotes an empty string. For transformation of an empty string, I need to do insertion. So it costs 1 because we inserted L. From empty string to Li, it costs 2 because 2 insertions happened, and so on. Now to character M, I have to transform it to an empty string, that is 1 deletion. So we have to add the 0 of this empty string plus 1. For MO transformation to an empty string, which is 2 deletions, and so on. For other cells, now for this one, D of 1 1, D of 1 1, we have to perform 3 operations. The deletion plus 1 will result 2, and the insertion plus 1 which will result in 2, and the replacement plus the distance between 2 characters, and for D of 1 1 and 2, it's insert and replacement. Finally, for the global optimal solution, we replace the M with I, the M with L, then O with I, and then O and ON remains the same, and lastly we insert and S which resides in an edit distance of 3. After finishing the table, the minimum edit distance appears in the lower right corner, which is 3. And that's all. Thank you everyone.